wait time we will use for another process. That's the basic idea of the CPU scheduling later. Then how can we address such a problem? We need to have the data structure to understand such a different state of the process. So we define the 5 states of the process. The first one is new. You can guess. New means it's just executed and before ready. Ready means the next one is the ready. Ready means it's everything is done. So out in ready to be called by CPU. So if your process in the ready queue, at that time we use the queue. Queue is the data structure. First in, first out. So when we have the multiple process in the ready queue, process A, process B. So process will be selected when CPU is idle. Then next one will be B, and so on. So that is a ready state. In when the process, after process is executed, so which means it's a new. Then if everything is done, which means allocate the memory and be ready to be called in the ready queue. That is the ready state. Then if the process is called by the CPU, that is the running state, active state. Until the terminate? No. Sometimes that process, in the middle of instruction, call the data from the file or other devices. So it will be waiting time. So it will move to the wait state, wait queue. At that time, CPU can call another process from the ready queue. Right? Ready queue, then this process state will be changed from the ready to running. Then if everything is done, it is moved to the terminate. So to understand details of the process state, this diagram shows a very nice. So new means new is just created or code executed. So there's a new. Then if that is everything is fine and be ready, that is moved to the ready queue. So that it will be moved to the, it will be called by the CPU. Actually, not CPU. Who is in charge of to select the processor from the ready queue? Operating system. And among the process in the operating system, there is a scheduler. It's called the CPU scheduler. CPU scheduler will select the next one from the queue. Then it's running. However, if there is I/O, then it will move to waiting state. Okay. Waiting is just wait until when? Until this controller return the data. How can this controller return the data? Interrupt. Okay. Stop CPU. I'm ready to send back the data I. Then CPU will get this data and process it. So that is the reason it's moved to the waiting, then ready, and call back to the running state. Also sometimes, even though there is no waiting, the input and I/O, no wait, it can move back to the ready queue to share the CPU resource with others. Okay, yes.
Is this where we use the pipelining concept?
You can use a bunch of other data structure, especially in the CPU scheduler. It's not pipelining. Okay? Pipeline means it's a kind of stream and it's automatically moved. But this one, sometimes the process in the running, it can be ready, also it can be terminate, it can be wait. Okay, it's not pipelining. Okay, but this will be controlled by the scheduler. So we will have another chapter for scheduler. Why? Nothing special. CPU scheduler just pick up the process from the ready and change the state that will be running. Sometimes move back and I will wait. Then why we need the separate chapter for scheduler? It's not that simple actually. For example, if we just pick up the first one, because there's a first in, first out. The queue is a big one. Next. I have very critical processor. For example, the virus program, antivirus program that should be running background. They need get the CPU whenever there is an input data or any input string. Okay, should get the CPU resource. But if there is a many process in ahead and virus is right now here, antivirus program cannot be run. Even this one should, depending on the policy or operating system, this cannot be executed. Why? This should be investigated by the antivirus program. So, not always a first in, first out. We need to consider different the algorithm strategy. There are many different algorithms. You can think of the first in, first out, and what else? You can give the priority, right? So this one is the first priority, this is the last priority. If you have the very lowest, very bottom priority, you cannot get the CPU resources. So you need to address such a problem. This is called the starvation. Starvation is usually the problem of the priority value. It's the algorithm, not only for scheduler, but any other. So we need to increase the priority certain time or feedback phase. It's some very complicated. It's one of the, it looks like the query processing algorithm in database. Okay, one of the most important algorithms, how to schedule dispatch such a process to get the limited CPU resource. Okay. To do that, actually CPU does not move entire process, this one into the queue. No way. Sometimes it's not like the 32K byte, it's much bigger. So for example, I allocate 1 gigabyte for virtual machine for heap size. So 1 gigabyte move to this data structure, no way. Instead, the handler access how the CPU scheduler operating system manages such a process using only important information, critical information of the process, not the data, not all instruction, but certain part of the data that such an important part. The information about the process will be stored at process control block. Process control block is another data structure, so much smaller data structure that represent, that describe your process. So your process actually will stay here, will be staying here until it is terminated. No, even after terminated, finish it, it may be possible this process is still in the memory. At that time, memory management, the algorithm will take care of this part. Whether this we need, if you have enough the memory resource, you don't have to, because it takes a time. So you can stay there, even though this is terminated and finished. But if there is no available memory resource at the time, even though this is ongoing, from time to time, back and forth. That is the main part of the memory management. How? The entire process by process? No. Instead, the time we use page. So page is another data structure. It's the I/O unit of memory management. Usually it's a 512 byte or the times of that. Okay, that is the reason when you measure the performance of your operating system, number of page input and output is critical. So you know the memory is very important to speed the performance of your system. How can you measure whether my system is busy and need more resource? You can count the page for it. Okay, we will see in the memory management later. So what kind of information that PCB include? This one. The first process state that we just discussed. That information is stored at the one of the PCB process control block part. And also program counter. Program counter is also in the text part of the process. Is the register information. Okay. Then, so location of the instruction for the next execution, because it's a stop and resume, stop and resume. The process, the data cannot be in the register. Instead, it should be flushed every time. Then, that information is in the PCB. Also, CPU register means in your CPU, we have the number of registers. This register of 0, 1, there's a reason, and you know how to use each register. There's a data, there are data. This data should be flushed out. Okay. Do I need to run all again to get such a data? Just copy, then store it at that part, PCB part. So that can be copied again when this one is active, running state. Okay. And also CPU scheduling algorithm, the CPU scheduler. For example, this CPU scheduler consider priority. What's your priority? The CPU scheduler check the CPU scheduling information, like the priority or the queue pointer, something like that. And also, as I said, it's very closely related to the memory management. So even PCB include the memory management that can be used by the operating system. Okay. And accounting information, I explained about what is accounting information, like how much this process use the CPU resource or I/O state. So you can limit the maximum usage of the CPU, like this process. Even though this process is very busy, it can take only the 50% of the CPU resource. How can you limit such a thing using accounting information? Also nowadays, this accounting information can be used for billing. Billing of what? Like the cloud service, on-demand service. So you have one big server, and I have the 100 customer. They can share my system. How can you charge it? In your electrical bill or the utility bill, it can be based on your usage. How much you use water. Similarly, how much your process use. So even though I run the 100 process, but each process use a little bit the CPU resource. It's a very simple program. That is different from the one process takes the all CPU resource, like the infinite loop. Which one? Definitely the second one should be built a lot. How can you manage using the accounting information? Also I/O states information, because which data is during the I/O wait state. This PCB should know which data is waiting and where is it, each device. So that is a I/O state info. Not, it doesn't have the instruction itself. It doesn't have the temporary variable or global variable, but only the important information to be managed by the scheduler and operating system. Then, how can CPU, your operating system, switch process by process? Suppose that we have the two processes. One is a process 0, another one is a process 1. Okay, so right now process 0 top, is the starting time and this is the ending time later. Okay, so this is a timeline from top to bottom. So first, the process 0 is executed, so it's running. Then it processes the instruction by instruction. Then at that time there's an I/O reading a data, request for the reading of data. So it's their state of the process is changed from running to I/O wait. At the same time, it should update the process control block PCB of the processor 0. That is called here PCB 0. Okay, including the process state and scheduling information, everything that we discussed before. Then from the ready queue, the CPU scheduler select the next one. Not always the first one. It will depend on the CPU scheduling algorithm. Then, if suppose that process 1 is selected, then at the time process 1, your operating system CPU scheduler with the PCB. Using PCB, you can replace the register information by new one, process 1. Okay? Then CPU scheduler knows it is a priority based, what is a priority, and also it knows where's the next one. 101 is the next instruction to be executed. Then process it. Then if there is the interrupt signal or something I/O or something the maximum time of the CPU, then it can be the idle, then the information about the process 1 are copied to the PCB 1. If scheduler select the process 0 for the next process, then we can resume the process by using the PCB of the process 0. That is called context switch. So context switch, do you think context switch is better for the performance or not? The more context switch, the better performance of the system? No, definitely not. Why? If we change the seed every time, it takes a long time. Okay? So usually, before I start the midterm final exam, I change the seat, so move the left, right. So it takes a long time usually, comparing to the nothing change. So, but we need context switch for what? Time sharing, CPU time sharing. So you should be smart. Not always every time CPU either context switch, but you need to do that. So you need to adjust find the optimize. It's kind of optimization of your system. Okay, what will be the maximum time of using CPU by one process continuously and so on. So context switch, you can actually measure. You can find such information using the system monitoring tool, how many context switch are happen. If too much happen, that's much bigger than expect, you need to find the problem. Anyway, PCB is what? Data structure. So this is the data structure defined in your operating system program. Okay? So this is I think the header file. You can find such a header file from your source code, kernel source code of your operating system. So you can see, so for example, counter is defined as a longer long, and priority is long, unsigned the long is a signal, and so on. This information are much more than we discussed. Not all of the data are filled. Some of them are used. also depends on the operating system. The data structure and the names are different. However, if you build a compiler for the specific the programming language, you need to definitely know such information. What about the thread? So you use a lot the thread. What is a thread, by the way? Thread.
Kind of a process.
Kind of process? Yes, it's a kind of process. It's the same as a process? Definitely not. If the same, we don't have to worry about mention about the thread. Thread is, as name implies, it's kind of thread, right? It's a thread.
And the exception?
So, for example, when you take a look at the series of the instruction, it's kind of thread of instruction. So, process itself is a thread. It's called a thread. However, the difference between the thread and process is in one process you may have 2 thread or 3 thread, multiple thread. Even though this is one line, logically, it can be, for example, multiple thread of the instruction. For example, if my program is processing the video frame. How many video frames? We have so many video frames. From this one, I'd like to get the average color of red. So you need to read all the value of the images, then average color. Algorithm itself is just the same for each frame. So you can process this one sequentially. What if we can process this at the same time? We create the one process for this, one process for this, one process for this. You can do that, but process restore different house. It's very hard, not hard, but it requires more resource, expensive to communicate each other. Instead, within one process, it's a one process, but only this code, computing average color value, will be parallel, kind of. So we can have multiple thread. It can be considered as the separate process. Okay? But some of the information are common. So actually, in terms of process, it's one process within one loop, but different section. They can be independently process the instruction. Usually same. So in your Java program, you can create the thread, then you can process separately. You can get the benefit of, you can maximize the CPU resource by creating thread. This is called the threading program. Sometimes you may not realize whether I create the thread because your programming language itself automatically create such a thread. You don't have to worry about it at that time. So in case you have the multi-core or multi-processor, you can get the benefit of such a multi-core, multi-processor. So by using the thread also. So in your programming, the parallel program language, you probably use such a thing.
Professor?
Yes.
So threads share the same stack and heap?
Oh yes, we will see such information. What kind of information will be shared? What kinds of information are independent? In the next chapter. Okay. Program, you can imagine global variable, which means heap will be shared. Right? No, not heap, the data. So text part should definitely share. Okay? And the program counter will be shared, but the local variable, the heap, stack will not be shared. It's independent. Okay? So we will see details about the thread in the next chapter. So in the programming, in terms of the programming or the structure of such a process in C program, this is the representation of the process in Linux. So it has the process ID. It's called the T_PID, process identifier. So you can identify the process ID, not by name. Okay, name is actually for human being. Okay, the 111 is not better than the process lead. Okay, I can easily recognize which process which one. What about the file? File is the same. Even though you create the file, then the rename into the processor lead, but actually in operating system is saved and considered and accessed by using file descriptor. Okay, everything is actually file in operating in computer. What about the network? Network connection, when you create the network connection, it create file descriptor. When you make something, the data structure, it create the file descriptor. Using that file descriptor, you can access, you can call, you can do something. So process is identified by the process ID and it has state and something like that. Then our goal is to schedule such a process. We will discuss about the specific algorithm of the schedule, CPU, especially for CPU scheduling in the separate chapter. Here we will see overview of the such a process scheduling. There are two types of the, but before that, what is the goal of the such a process scheduling? It is maximize the resource, especially for the CPU resource. So we are going to maximize the CPU resource, CPU use, okay? Then also quickly perform the context switch. So there are two types of the CPU at the process scheduler. Okay, one is the long term, another one is the short term. We will see detail. And also, process maintains several different queues of the scheduling. The job queue is the old process will be queued in this structure, and ready queue, as we already saw many times. Also, each device has the queue device queue. Why? It cannot be accessed at the same time. Old process, this controller, device program, or your operating system should control so each process can access the such a device, especially for I/O device. So this slide shows the some available queue in your operating system. You can see queue is nothing but actually I think that you guys already create such a queue structure in your data structure course or algorithm course. You can see we need only the pointer of the next one, and also you should know where is the end of your queue. Okay, so it's nothing but PCB because we don't have to worry about the entire process, instruction or whatever. Instead, we can manage only the PCB. And this is the, for example, the disk device queue. So currently PCB3, and next one is PCB14 and PCB. So this is process 6, process 14, process 3. They are accessing that device. And for example, terminal, in terminal, the PCB, the file process is in charge of such a terminal. It's kind of probably it's a shell programming. So this is called the queuing diagram. Okay, so from the ready queue, the ready queue where the CPU is ready to get the CPU resources, and the CPU can select at the PCB. The process will be selected by CPU. Then for a while, it will be either IO request. Okay, so will be wait, IO queue, and the time slice expired, which means the maximum CPU time for each process. And in case fork a child, at that time fork, what is a fork system call? Create the child process, which means copy the parent process, current process, to make the child process. At that time, CPU cannot do any other thing because it's stop, almost stop, then copy the process itself, right? You cannot process the instruction. So which means it's during the fork a child, it will be CPU will be stopped, and the other interrupt signal. Okay, it will be either one of them. Then after we complete it, it will go back to the ready queue. There are short-term scheduler and long-term scheduler. First, the long-term scheduler is called the job scheduler. Usually, it will decide which process will be selected. Okay, each process should be back to the ready queue. Okay. What about the short-term scheduler? Short-term scheduler is frequently happen in time slice. Short-term scheduler focus on how to allocate this piece of CPU time for the process in the ready queue and select this one. So CPU scheduler, when we are saying the CPU scheduler, that is a short-term scheduler. Okay. On the other hand, the long-term scheduler is which process will be back into the entire process is back into the ready queue. Usually, the long-term scheduler is control the how many process will be running at the same time. So there might be a limitation at the same time of the number of the PCB in the ready queue. So if your operating system with the specific hardware that can process many processes, you can increase the number of processes in the ready queue. That means that determines the degree of multi-program. Then, that doesn't mean you have the 8 process in the ready queue. That doesn't mean you can process 8 at the same time. You need to share the CPU time. For this, how can you do that? Using CPU scheduler. Usually, most of the time, this is very quickly done. Okay, but this one, long-term scheduler, is just to select which process will be selected to this. Not very frequently, but from time to time.